Okay. Can you hear me? Yeah. Welcome everyone to the Haskell Exchange. Anders Lø. I have helped together with Oliver Charles and Frederick Olsen and several others this year to put together a good program. And I hope you're going to enjoy it. I have to make two announcements before we can really start. The first is that while there haven't been yet any program changes, there has been a room change. So we have 3 tracks, and the second track is labeled to have room name shift, and it's actually taking place in Alt-Tab instead. And if you look at the final page of your programs, then you'll see where the rooms are, but they're all easy to find. The other announcement I have to make is that you're very welcome at all times to give feedback to the organizers about how things are going, and there are feedback forms available outside of all the rooms. Okay. So now it's a pleasure for me to introduce the first keynote speaker, which is Don Stewart. Don Stewart is, well, I've tried to get him to speak at the Haskell Exchange for several years now, and he always declined. So there used to be a time when Haskell was still relatively new for me, where Don appeared to be everywhere within the Haskell community. So he wrote all the important libraries. He wrote 80% of the emails and blog posts and Reddit posts of the whole Haskell community, and then he suddenly disappeared. And that was when we moved to Standard Chartered, and I think today he's going to tell us what happened to him there. Okay, thank you. Welcome.
Right, so yes, so for the last 6 years I've been working in finance using Haskell in New York and now in London, and this talk is sort of a distillation of what I've been up to. I've been using Haskell for about 18 years now, since the very first course I took at university was in Haskell. And things have changed a lot since then. And one of the themes of this talk is that actually a lot of the stuff that we did in the 90s is still really the core of how to be productive in the language. So the themes today are how language tools can help you make better software. I'm interested in building software. At StandChart we have a lot of trading software, and we use Haskell for all sorts of different kinds of things, small and large systems. And we do that with a relatively small team. And we want to ensure that we're using our language to make the code maintainable. So I'm not being bogged down in maintaining stuff. I want to be able to reuse and iterate very quickly and throw ideas out and combine them and mix them and just make everything very flexible and liquid. And ultimately, we produce cheaper software this way than doing it through some more traditional IT, large enterprise procurement and spec and development processes. So we're trying to really do something different. And so I'm going to talk about how we use the language to do things like reducing latency, making code faster, making code more robust. And ultimately, it boils down to keeping things simple. Don't try to be too fancy. Functions and data types, start with that. And if you can build it with that, Haskell 98 really is the core. So what have we got? About 3.5 million lines of Haskell. There's 3 million lines of Mu, which is our in-house version of Haskell. And that exists for a couple of reasons I'll talk about. We've had about 150 contributors, about 150,000 commits. So we have a very large repository of Haskell code. And it's not just a monolithic system. It's many applications, layers, libraries, preludes, and things like that. So you mentioned an entire ecosystem. We use 2 Haskell compilers. We use GHC for pure, real Haskell stuff that's standalone, and things that need to do more finance-y, quanti stuff, we use Mu. And as I said, it's used everywhere. It's real-time pricing, it's risk, it's data analysis, data visualization, GUIs, web services, really anything in the bank that needs doing, we can pull Haskell into to solve the problem. We run on 2 systems, Linux and Windows. We run on clusters and grids and small machines and big machines. And in lots of countries. So this is Haskell at scale. We're going big here. So I'll cover some of the techniques, some of the reuse, and some of the lessons. It's essentially about the lessons. I can't show you the software, but I can talk about the things that we've done and the patterns and how I try and encourage people to write the kinds of Haskell that they write. In particular, we're trying to integrate into larger system. You've got a 100,000 person company with very old code, very new code, code written in different languages. There's Scala, there's Java, there's .NET code, there's C++, there's C, and then there's Haskell stuff. And so you want to play well in this ecosystem. And there's other things besides. There's probably some COBOL somewhere. All through managing complexity. And so we're a small team. I've got 25 people programming Haskell. I'm hiring, so we're trying to get to about 35 this year. It's a small group of software engineers in a very large organization. So the organization as a whole maybe has 300, 400 developers, possibly more, doing Scala and .NET and other things like that. But we're sort of 10% doing Haskell. And our mandate is threefold. Deliver very quickly. So we're used when somebody realizes they need something in a day or a week or 2 weeks, and they can't go and sort of procure a team and hire for it and have someone spec it for 6 months. We get pulled in when it has to be fast. And when delivering it fast means it still has to work, because it's still trading software. It's still potentially producing prices or risk or regulatory concerns. We need to do robust systems. So if we're shipping it the same day, it better work. Otherwise, there's no point, right? It has to work when we ship it. If we think we're done, we're done. So even with, and this is even when the infrastructure you're running on itself is problematic. So you might have poor latency. You might be running code in Mauritius or something over a satellite link, and there's going to be very bad bandwidth. There's going to be very bad latency. So you need to be able to ship something to this guy who is probably not ever going to talk to you, and he's going to run something, and it should be intuitive, and it should work. So plan for that. Build systems that users trust is kind of the theme. You have to be so reliable, it should start quickly, and it should just work and do the core things really well. And then you build trust, and trust leads to more projects, bigger teams, and more Haskell code. And when you're a small team, you have to automate everything. So you cannot rely on other teams to do testing for you, or to do your releases, or to monitor your things. Automate everything so that you don't have to do it, so you can sleep at night, and then you can get back to shipping more code the next day. And over time, we've ended up turning the company into an API. So any service that's offered internally, we essentially write a Haskell binding to, and that gets used on one project and built and extended, and you build a huge ecosystem of APIs that script your organization. And that accumulated productivity benefit means you get cheaper and cheaper over time. So the first projects were more expensive than projects today to do the same thing, because we reuse a lot. So we try to invent new things. That's one of the things that we try and do as a Haskell team is solve problems where they don't really know how to solve it. So there's definitely research problems here that we get pulled into, or just there'll be a financial problem and they need a computer scientist to have a think about the appropriate techniques. And when we've got APIs to things, we find ways to compose and glue together parts of the bank that didn't realize they could talk to each other. So you can pull things from one database and talk to one trade processing system, and pull market data from some group. And none of these groups talk to each other, but the Haskell code is the glue between. And that puts us in the middle, able to synthesize and create new products just because we have the advantage of seeing everything. And we're often working from very informal specs. So the model is that my team sits on the trading floor and talks to the traders, or the traders talk to us, or they shout at us, or they call at us from across the room and say, come run over here right now. And then they'll say, it's doing this, I need it to do that. And you've got 3 minutes to work out what it's supposed to be doing. You hope you've got logging in place to capture whatever thing just happened. And then you can go back and think about what he really meant and turn it into a bug report or a feature request, code it up, deploy it, ship it, and he runs it the next day or later in the day. That's what I mean by informal specs. So you don't necessarily have any professional requirements gathering. It's just you talking to the trader, trying to understand and then build something. Sometimes these systems are very small. It might be just for 1 or 2 people. It might be for 600 people, built from many little bits of feedback. So we're doing a lot of, it's all around fast iteration, building Haskell stuff that doesn't break, and letting you move very, very quickly, which avoids a lot of the overhead of software development. And then finally, the team has to have a high success rate. This is what I've been spending 6 years working on, is trying to build the team to be like this. We have to demonstrably outperform the Java teams and the Scala teams because we're doing something a bit more unusual. We're using Haskell. And we're hiring PhDs and master's degree students and bachelor's degree people who only know functional programming and computer science. They don't know any finance. This is very unusual to have a team with nobody with any financial experience running some of the trading software. So you have to be better, you have to be faster, you have to be able to do it again and again and again. You can't just be one trick and that's your app and you can't grow from that. So you have to be able to have a pattern and a model that people trust that given some random project you can do it. So we try not to be the incumbent, we try to be always lean and looking for new things. So what's our toolkit look like? Well, we have Cortex. Cortex, there's a few papers and bits and pieces of it, but it's the enterprise prelude and base over a quant library. In finance, you have quants who write pricing models, Black-Scholes and things like this to price products. And then you take these products and you have representations for them as contracts, and you glue them together with risk scenarios, and that's essentially what finance looks like. It's a bunch of pricing models for products, which are derivatives contracts. You need to glue these together because an equities quant doesn't talk to an FX quant who doesn't talk to a rates quant. They all do different things, and they think of themselves as each as special individual specializations. So you glue them together with a language, and people use, different banks use different languages for this. People used to do in-house stuff, slang, famously, in the 90s at Goldman. Now it's more Scala or Python or Haskell. So we're using Haskell at StanChart, and we use our in-house Haskell so that we can talk to C++ with lower overheads than if it was GHC. That's essentially the main reason, is we want to be able to call into some quant C++ code as if it was a primop in the language. So very cheap. And then on top of that, we build APIs to all the systems. So you've got a pricing function, you can price a product and a contract. What do you do with that? Well, you have to take trades from somewhere, you have to get market data from somewhere, you have to book it somewhere, you have to generate PDFs, you have to generate data, you have to generate reports, and then the product's booked and running. And you just do that again and again for millions and millions of trades. Maybe hundreds of different products, and running in different jurisdictions, and each one is different. So there's just endless levels of specialization once you get the core right. And so the core is our Mu compiler, one of Leonard's many Haskell compilers. He's written a few of these over the years. This is a good one. It's a whole programming optimizing compiler, which lets us get away with it being bytecode interpreted. So it's not as fast as GHC, but it does optimize the world. So we build all the stuff together. It's largely strict. It's not fully strict. It's a bit funny, but it does mean you don't have you have to turn on recursion and you have to turn on laziness. They're not on by default. This makes the Haskell people who use it grumpy because they generally want to write control structures. But you can survive. It doesn't really change the flavor of the language at all. The core thing is functions, pure functions, and data types, and having side effects removed. That's the core essence of a Haskell implementation. Importantly, it's portable, so we can generate a closure, we can serialize something, generate a closure locally, ship it to a completely different architecture, and continue executing it. So it's a cloud model. It really is a very, very mobile code. So I stream my stuff from Windows and move it to a big grid somewhere to do some large computation. We're spending a lot of time looking at cost models to work out where to execute the code. How many CPUs I've got locally, how far away is it to the next bigger compute center, and then moving the code where there's enough RAM or CPU or latency, basically. And it has a lot of dynamic typing. So we use any, which is like dynamic plus typable. But it's there on the edges of things so that you can quickly get some data in and then impose a type structure on it. But you have to be careful with it because it tends to infect. You can be, as you know in GHC Haskell, dynamic can infect things. So we do all the usual things. We use quick check. We use lenses a lot. We've been using lenses heavily since early days because a lot of what you do is edit contracts and edit data structures that represent things in finance, and you edit using lenses. And we use parsers and so on, and Cairo and stuff like that. And things that we do a lot ourselves in the industry, I think, is data visualization. GUIs, we have to generate a lot of desktop apps and web apps increasingly. So the actual trading software that's sitting there on the terminal blinking numbers at people. We spend a lot of time doing memoization to try to cache things. So you're trying to minimize recomputation as much as possible, minimize transfer of data across networks. I can't move data between Singapore and London a lot. It's expensive, so I need to cache a lot. So we use purity to enforce that. If you know an object can never change, and you know exactly an identifier for that object, you can cache it and just refer to the local copy. We generate lenses, we generate bindings to lots of things, and we have an amazingly good time and date library. because everything is about time zones and date times and knowing if it's a leap year or if it's a holiday in Taiwan because a typhoon just occurred. So there's a common refrain is that all the bugs are actually calendar bugs. The Haskell code works, it's really just knowing if it's a holiday somewhere that's the key. Some other things, we wrote our own haddock. We have a very cheap logging system so that we can just add essentially like a trace message or log message to anything, anywhere. It gets written out asynchronously, scooped up in batches and sent to a central logging system. So I can just add real-time logging to anything that running anywhere on the network and start to see messages flowing in. So that means we can monitor stuff as it's happening. And I encourage people to be able to write logging so that you can diagnose any problem remotely without having to talk to the person, because the trader's probably not going to give you very good information. They're just going to say something went wrong and the number's wrong. This number here is 7, it should have been 7.2. Okay, how did I get that number? You need to trace it and log it. And then surprising things that have turned out to be valuable, process isolation. So we have a lot of systems that can fail. If you're writing something that should be pricing 24/7, it needs to keep running. So we use process isolation to wrap up Haskell processes and monitor them, restart them, kill them. If they deadlock, if they crash, if they lose resources, databases go away, servers disappear, transatlantic cables get cut. Well, not so much, but trans-Pacific cables get cut. And so we wrap this stuff up in a process and monitor it and restart it, and you can build very reliable systems this way. We often use processes just to enforce memory boundaries. So if you need basically constrained regions of memory that you can allocate into, a process is a pretty good structure for that. So fork a process, set it can have 1 gig, it can allocate whatever it wants, it can segfault, who cares, I don't care if it gets me a result back, then I'm good. But it won't kill my machine, and I've got it in its little sandbox, and I study it, and then time it out if it fails. So we do this a lot, and this is something GHC could really use. We use process of parallelism, for example, to just make copies of a function, run lots of things simultaneously, let the operating system do the scheduling. And we use an in-memory relational algebra data type. So there's a paper at ICFP on adding a type system to this, or at the Haskell Symposium. So you have data, and it's structured, it's tabular. Relational algebra is a very good way of looking at this. So I need to join say user IDs against names, or I need to look up things from many different databases, I need to do joins. And I can't always issue direct queries against databases for this, and I don't always have a federated view of databases. But I have relational algebra in memory. So instead of, we often use it for things that you would almost use nested maps for in GHC. We would instead use relations with many columns, rows, and then joins. We use it for data mining and analysis. So that's the kinds of things that we're doing. Why are we using Haskell at all? Well, we want to build big systems, and we want to build it cheaply from small systems. And we want to be able to keep building for 5 years, 10 years, without being swamped in our own maintenance. So we almost spend no time doing maintenance. Essentially, the type checker building each night does the maintenance for you. You can't check in anything unless the whole world type checks. So you keep the whole world type checking, your code maintains itself. The bits that don't are, services come and go, and you have to switch off a database here and turn on a different host there. That's the level of maintenance, but it's not actually going into the code and refactoring APIs. We're doing a little bit of that continuously by keeping the whole world type correct. And so in a normal system, the complexity of this huge 3 million plus line thing would dominate. But instead, it's Haskell, so it's many small, pure APIs that slot together through very constrained paths, just pure types. You know exactly what they export, you know exactly all the instances that it's used, because we can see the whole world. And the maintenance becomes, sort of you just keep it type checking. And this has proven to work. We have developers come and go, people work on one system, they hand it over to another person. As long as it's type checking, you can essentially maintain it. As long as it's written in fairly simple idiomatic Haskell, at least fairly simple Haskell, you can maintain it. It's when people start doing complicated things and exploiting compiler tricks and type system tricks that you start to reduce the number of people who can modify the code. But even if they try to modify it, it should still type check, so it's not too dangerous. So the key lesson of why we use Haskell is to control complexity. We want to minimize the ways components can interact. A very good way to do that is to ensure that only pure components can talk to each other. There's no poking around in each other's memory. and having strong types with side effects, so I know exactly what pure code I can call, and that just essentially works forever at that point. So any steps to reduce or restrict the interactions between components pay off long term. So simple APIs, remove functions, certainly remove I/O, remove any kind of unclear types. If it's a double, make it into a new type. Make the contract between components clear, remove the number of spaghetti interactions with things through side effects. And certainly, we would never do anything like expose mutable state. You just wouldn't even do that. But even I/O already starts to become non-modular. And because we don't have time to do a whole program rewrite, I can't rewrite 500,000 lines of code and make changes. Leonard tries to occasionally, and it's always interesting to watch those Git commits get merged in. But we try not to do it too often. And so we want to prevent these unnoticed interactions. And so we're constantly also looking for tools to enforce this. So we ramp up the number of checks we do on each commit as we realize there are idioms that don't help us. Okay, so we're using the language here and we're using the machine to catch mistakes earlier, to enforce our design assumptions, to document the designs, to limit unintended interactions and make wrong code impossible to write. So how do we do it? Well, the main thing is types. APIs become self-describing. Any dev can build something new reusing an existing API as long as they get the types to fit together, like jigsaw puzzles. You can take people off the street, and as long as they can read the Haskell type notation, they can write something useful, and they can't really break things. I hesitate. You have to be novice users can't break things. Power users can break things because they know what to exploit. So that's the dangerous thing. If you've got someone who's very senior and knows what they're doing, they can really make a mess of things. But a junior person basically can't get anything working until they get something working that's useful. And that means I get to sleep at night and I can hire people and just give them something to write. And I know that often a new joiner will say, oh, is this going to book something here? Is it going to generate something here? Is it going to interact with anybody else? Am I going to break something? No, you're in your module and you've got your type signature and there's no I/O. So you're safe. You're in a sandbox. And that person feels more secure and can start experimenting. So that's how you scale the team a little bit. And so the types start to pay off on the large systems. On a small system, you can write a type-correct program with no types, right? If it's 50 lines, maybe. If it's strings, you can kind of get something working. But once it's 1,000 lines, once it's 50,000 lines, once it's 500,000 lines, you absolutely cannot hold that in your head, and you just have to start walling off components with types and saying they only interact through these known signatures. And you've captured the architecture of the application in a machine checkable way. And so we ended up sort of locking down components like this. You might iterate very quickly and have fairly loosely typed. You might be using doubles and bags of things and maps and stuff. And then you start to refine it as you know what your design is. You add more type system features. You add phantom types. You add singletons. And you start to control and really codify the architecture in the type. And then there's only a few ways to write things, and anything else doesn't work. And that way you enforce the architecture. And this is a step down the path to actually more formal methods. So I'm interested, and we are always trying to find ways to add a little bit more rigor to the types and a bit more expressiveness. And this is not, so the talk here, this is a talk I've given to other non-Haskell audiences. So for you guys, you know what this stuff is, but it's useful to restate, I think, that it's about the simple stuff. The simple techniques that we've had for 20 years, 25 years, 30 years, are enough to do incredibly valuable things, to bring real value to an organization just by ruling out I/O and controlling it, by having new types and things like that to tag semantic entities. Everybody else is just using doubles and strings. So you already win if you can tag, instead of writing double, double, string, double, which is what a non-Haskell person would write when given a function, like some kind of pricing function. It does something with some numbers and some symbols. This might be a holiday calendar or something, and it returns some number. Right? It's all about numbers. So if you're a numerical person and you've got a physics background, you just think, okay, doubles, arrays of doubles. That doesn't help me write new code against this, because I don't know what these doubles represent. They're too rich. So it's this stringly type programming where I've lost information about what these things represent. So there's an erasure of information that would have helped me. So what we really tried to do is tag the semantics of these things. We don't care about their underlying representation as much as the meaning to us in the domain that we're working in. So we'll have a LIBOR interest rate, and we'll have a $SING spot rate, and we have a date. and we're going to compute the SIBOR, which is Singapore LIBOR interest rate from this. And that would be the typed version. So to compute SIBOR, I need the US LIBOR rate, and I need the Sing dollar spot rate, and I need the date. And that's a much better signature. And that's a signature that's specific to my application, and I'm not going to break it by getting, for example, the doubles mixed up. Use new type and data to distinguish unique entities in the system. Something we see sometimes is somebody will write a quick draft and it's got a lot of doubles and strings and overly rich types. Then you make it better by just sitting there and refactoring and changing one type to a new type and watching for where the type errors are, and you understand where this information flows through the system. And so you safely refactor it into a more refined version of the spec just by changing a type, tracking down all the type errors. And it's a type checker-driven development model. And eventually you've got a very good spec encoded in types, and you've disentangled all the different semantic entities by following their information flow through the program and letting the type checker discover all uses. That's an extremely valuable way to keep code maintainable and self-documenting. So we do things like this: lift strings, tag them, specify the number of decimals we want to show something. Traders are obsessed with the number of decimals. It drives them so crazy. If you put commas in the wrong place, or you don't put commas, or you show them 7 decimals, and like, that's stupid. It should be 3. It's obvious 3. Okay? Or it should be multiplied by 10,000 or by 100. These things are not, as a programmer, you're like, okay, sure, that's fine. But they really care about it. So we actually have libraries for this, of just getting the display right at the type level. So we lock the printfs into the type system. So make it impossible to mix up values, because everything's a double. In finance, it's all doubles, and strings. Make it impossible to mix these up. And then we add phantom types. So we start tagging these things. So it's a 3 decimal ratio, or it's a sterling ask spot price. And so there's fewer ways. I can't get bid and ask mixed. So if I'm offering a mid price or a bid and an ask, these are separate entities, and you really don't want them to cross. And it's stuff that's obvious to people from a finance background, and then we just put it into our library, and then any Haskell programmer can get this stuff right as well. And we all look like we're great at finance. But we don't really know what we're doing beyond understanding these entities, tagging them, structuring them, encoding them in the type system, and formalizing them as we go. So we formalize practices that are implicit. Another one that catches us a lot is Boolean blindness. So a Boolean on its own tells me nothing about what it is, what predicate is true and false. I just know that something was true and something else is false, but I don't know which way. And getting this inverted is really, really common. So it's very common to do things like take a type like this, IO bool, and turn it into something much richer, like, oh, this is the type signature of authenticating somebody. I've got a username and a password, and bool, they're authenticated. Or bool, they didn't authenticate and they were false. Probably it means authenticated, we think. But here's a much better way to say. I've got some privileged user P. I take the user and I take the password. I authenticate them somehow. Now I have an authenticated user P, and that authenticated user can only touch other things that take authenticated users. And so I've got sessions now for authenticated users bubbling through my system. And again, it's really simple stuff. It's really simple stuff, but it captures the important problems that people really care about the representation of data, how to authenticate users and keep them separate from each other, who can call what, and you don't need a lot of fancy stuff to do this. So as I said, start introducing new types for each thing. Test your assumptions about values that are distinct. If you think you understand what your code is doing, try putting a new type on naming something and then seeing what breaks, seeing where it infects. And that quickly starts to tease things apart. So that's the types, and it's basic use of types, and using new type a lot. Using new type for its semantic purpose rather than anything to do with its representation. The next thing is polymorphism. Write code that reuses is reusable. This is something you get an intuition because we have libraries of this stuff, especially for monads and so on. Compilers can enforce things when it's parametrically polymorphic. I don't commit to any particular representation. And this is really easy to do. It's really easy to write nice polymorphic code and generalize things. You just float it out and change a type to a lowercase type variable and see if it still type checks. And then you've either made a mistake or you've written some general code. Name a concept once, implement it, and reuse it. So we do this, you can imagine, for our control structures. We have our things that fork a process into a region and then time it out after some number of seconds or a number of retries. That's just polymorphic in the thing that it runs. Or you have computations that do something and produce an interest rate at the end, or some known entity, but they're polymorphic in the things they take, they gather and return things polymorphically. These can be generalized and reused. Alternatives, for example, we use a lot of, because you often have business rules and you need to make choices, and there's heuristics, and there's essentially an order of things to try. And this happens a lot in business code, business logic, because there's no algorithm here. There's just try a whole bunch of things, and you'll get better solutions that are close to the top, the rule that fires. So we use alternatives for that. And often it's to do with failing over. So you imagine you've got many different data sources all doing roughly the same thing, and there's some function to convert between them. So I can source market data from here or market data from there, or I can look at trading instruments of different kinds. And they're all convertible somehow to information that tells me about the thing I'm really trying to compute. The alternatives are great for that. So I can try my trusted source first, then I try some slightly less trusted, then I try some flaky source that's only available on Saturdays. But I end up building a stack of things that generally gives me more robust, gives me a result. Because the goal here is to have a result, have any number that's plausible rather than to fail. The worst thing is to have no number, because the trader can still trade, they just need information. But more abstract can mean more obscure, and this is where the simplicity comes in. So this is real code, const fmap, 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 fmap to any. Some f of a, some from a. So the any is dynamic, which is a bit worrying, and then there's fmaps over 4 different structures. You can only write this once, and there's no other implementation, so that's okay, it's not dangerous. But it's also not maintainable. If I tweak the stack, I have to go and insert types and deconstruct it and make it pointed and start naming fragments. So that's just write once code, and we stick it in there and forget about it. So I'm torn. You see this kind of code. So you need judgment about when to generalize and when to not. And you can go overboard with operators as well. So we have DSLs, and people write libraries of things to name concepts, and you can go a little bit nuts on the symbols. So this is some GUI code, real GUI code. But it's got non-intuitive domain symbols that they're just essentially symbols that you make up. There's no domain here that I'm capturing the notation from. I'm just coming up with new notation for no obvious reason. And now I have to go and work out what 3-arrow is versus 1-arrow versus 2-arrow. And arrows with different, so you end up with 17 different arrows. And I can never remember which one's which. And so I'm not a big fan of using lots of symbols, because they're just not readable. They're not self-documenting. Okay, and then the other big thesis here is that everything is a compiler or an interpreter. So it's all about data transformation, or implementing some semantics and compiling down to some richer semantics or less rich semantics. It's transforming semantic entities. So we write ASTs everywhere. You parse, you build an AST, you transform the AST, and then you compile it out to some other representation. Often it's simple stuff, but this is everywhere. And it gives you a framework for building almost anything. It can be written in as an interpreter of data to some other kind of data. And it structures an AST, transformations over the AST, and then some pretty printing phase. So we capture the deep rules about the system as an algebra. We work on this AST, which is the core of our engine that has some notion of introducing values, transforming values, eliminating values. And that works for simple to complex types. We capture the APIs of external systems like this. So ones you're all familiar with would be JSON, right? You get imagine JSON, but then there's 10 or 20 different crazy bespoke financial formats. So you give types to them, and you operate on those types, and you write a parser, and then you get it into some Haskell data type, and you work on the Haskell data type. Another one here, query languages. Query languages are very common, because you've got endless databases, old and new. They have all sorts of weird primitives of things they can search on, and so you encode that. And it has its own notions of booleans and its own notions of strings and so on. So you new type those, you give some interpretation to the Haskell equivalent and back. And then you write an interpreter to evaluate these things. So we often will write an implementation that you think is a good binding, then you symbolically execute it using quick check, and you generate random statements, and you check that predicates hold, that things are invertible or idempotent, or they have zeros, or they're monoidal. There are properties these things should hold. And that way you can have a very good implementation that only uses a subset of the features of the underlying hardware or software, but it's a trusted core that has really nice properties. And those really nice properties are things everyone on the team can then use and reuse. You've gathered the hard-won knowledge of the useful parts of the system to understand and baked it into a Haskell library. So we write these kinds of compilers a lot. And they're just translations from a rich typed version in Haskell out to the underlying system. Part of this is having total functional programming. So everything will go wrong. Everything will go wrong. Your disk will die. Your network cable will be cut in a country that you're not even working in. And your server will disappear and your database will disappear. Or the cable between the country you're in and the country you want to be in is cut. That's happened. So everything goes wrong. All the hardware errors. Their RAM just corrupts. Disks corrupt. Smoke comes out of machines. They make grinding noises. And your code has to keep working. It has to detect that it's not doing the right thing and somehow spin up somewhere else, or at least log everything to recover the session. So anytime you write underscore equals error help, that you're going to hit that at some point, because the cosmic ray is going to hit your code exactly on that branch as the branch is being taken. So don't write non-total code, write total functions. And move the partiality to the edges, to the parsers and so on. So you very early capture, oh, I can't handle this is an invalid state, and quickly reject it. But then in the core of the system where the complexity is being controlled, the Haskell part, it's all total functions, it's pure functions, talking to each other, and it's sensible, and that code is maintainable and robust and doesn't go wrong. But when it does, it's in a sandbox, it's in a process that's being logged and monitored and can be restarted. So you just have to be so paranoid. And the old hands who are good at software engineering in finance, these guys are really paranoid. They absolutely have seen every single thing fail. And so they run 5 copies of their stuff all the time on 3 pieces of hardware in 2 different countries, on 2 different data centers in each. And they have redundant everythings, and they log everything. Because disk is cheap, relatively, space is cheap. Compute time, not so much. Network, not so much. But you can log. Don't delete your logs. Don't destroy data, because you'll need to recover it. And eventually, something bad will happen. You need to know exactly what happened. So we lift all our errors. We try to avoid asynchronous things. We make everything total. We turn our partial stuff into total things using catch and so on that lifts it into an either. That's extremely common. And then you can be very clear about how to recover each error. Or you just say, this error's out, throw the process away, start a new one. We do property-based testing. Once you've got a nice AST and you've got the nice semantics, then you can use quick check. And you discover, it's amazing what you can discover about other people's systems by using quick check. So you write a model of their system in Haskell, and then you interpret the model, and you write tests that you think should hold, and you discover weird corner cases. And these guys, oh, well, we never really thought about that. Quick check is great for breaking other people's systems. We have to be very careful with it, because we do break other people's systems, and they don't like that. And they ask, why are you generating all this badly formed data? Well, we're just weird Haskell people. And so that there's a political negotiation about whether it's fine for us to generate random malformed queries to watch their systems break. At some point, you're not generating real value for your company at that point, but at least you know how these systems will fail and you can avoid them. It's all about gathering information about things. A lot of these systems are not documented very well, or they're only documented for the successful path, whereas you're really interested in the failures. So we can discover better APIs through this. So you write a model that you think is okay, you write quick checks, you make the quick checks work for you, you try them against the real system, and you go, aha, there's an assumption here that I missed. So it's a cheap way to do verification. Yeah, so that's it really. The big systems are built from smaller systems. The interfaces are mediated through compilers and interpreters. Interpreter-like Haskell code that maps high-level types into their lower-level representations. You keep the core of it as Haskell types understandable through basically Haskell 98. And you could be building systems like this. If you're using SQL, if you're using visualization, if you're using JSON XML, any of these things, they're all representable as just ASTs, transformations between ASTs, and I can mix and match them. There's a combinatorial explosion of apps and useful services I can write once I've got all of these things as Haskell types that just can be glued together. So I just take a bit of this from 2 previous projects, glue it together, add some visualization. That's a new system built in a few hours, whereas from scratch it would have taken a week or 2. So it's the category theory for software architects. I kind of joke about this, that software architects love to draw arrow boxes with arrows, and we just give the semantics to what the arrows and the boxes mean. And they're actually semantically rich, meaningful arrows and boxes. Yeah. So let's see. I've talked about types, and I've talked about purity, and about sort of the design approach of just follow the simple stuff, write everything like it's an interpreter for some abstract language. You still have to talk to the world. And so that's the messy part. That's where the hardware is, and the network, and the helpful IT guys who cut your Ethernet cables attached to the trading systems. Or they pull the plug out of the one and put it into the other because it looked like it was in the wrong port, but they weren't sure. These are all things that actually happen. So you need to capture I/O, and you have to reason about it and be very careful with it. So side effects like I/O are fundamentally anti-modular. When you have these things, you now are sequentializing your program. So there's less programs you can write correctly once you introduce side effects. They've added more constraints, and those constraints are not necessarily documented in the type. It's just an I/O. It does something, and you better do it in the right order. You can't reorder these things at will. You can't evaluate them at compile time, generally. Though Leonard would like to, and he may, if you talk to him nicely. It's hard to optimize these things. It's hard to parallelize them later, so often we just come back in and, oh, it's a bit slow, okay, split it n ways, calculate in parallel, and join. It doesn't work if it's I/O, you've now got to sequence it. So these assumptions about ordering and resource usage in side effectual things may be invisible. You may not be able to know the weird invariance this system has, that, oh, you can call these things in this order, but you have to put 200 milliseconds between each call because we didn't really think you would do it that quickly. These assumptions about resource usage will bite you. So we tag these kinds of things. We have, I/O, safe I/O, for example, is really useful. It's a read-only FX. That's a useful subset of things because there's many initialization problems. We just read in the data once, and it shouldn't change for the lifetime of the process. That's a very common pattern, and having a separate type for it is useful. You can reasonably disagree about what safe I/O means. It's not entirely clear. But just like the initialization problem and configuration problem in Haskell programs, there's a bit of I/O at the start, and then you freeze it. So that you want to tag that concept somehow. Effects are vital, but they are so powerful and they're so general, and they will tend to proliferate. If you start in I/O, people just tend to stay in I/O, unless they know what they're doing. So this is the pattern. I/O at initialization time, gather the resources. Now the core logic is just pure data transforms over strongly typed data. And you make it more and more typed as the lifetime of the program, as you maintain the program, right? So it starts off as just simple, naive data types, and you refine it using new types. You evaluate the result of the computation by interpreting it into some format that you flush to the outside world. So the I/Os move right to the edges, and you have a lot of core pure typed code that you understand, total functions in the middle. It's exactly the same thing I was doing 10 years ago with Xmonad. Xmonad's a window manager, it's peeking and poking at buffers, and it's executing all sorts of crazy asynchronous stuff. But it moves that right to the edge, and then interprets a model of the X11 command. It models the state of the world as a Haskell data type, and then it flattens that thing to a sequence of commands to move windows around. And that exact model of this I/O at the edges, interpreter, and model of the data type in the middle is everywhere. It's absolutely everywhere, and it's a really good technique. You just bang these things out, and you have more semantics than the competitors' systems. They've written a nice API, but it's not an interpreter, and you can't just quickly retarget it to many different things. There's huge benefits from this. So we can do, we know exactly which code can be executed in which order. And this is a fundamental advantage to a Haskell programmer. They have a core chunk of pure code that can be reordered at will, and it can be very quickly changed. And the I/O stuff is really tagged, so they know exactly which parts of the system are going to break, and you make that robust. So it's a fundamental advantage a Haskell programmer has, is that their side effects are tagged. So ultimately, you have an API with no surprises. That's the thing, is reduced surprises. Every surprise is something that the guy who wrote the code knew, and the second person who takes over doesn't know, and it catches them. So don't surprise people. Don't bury surprises. So then how do we make things fast? Well, we're using Mu. Mu is an interpreter. It's like GHCI. It's basically, or like Python. It's a bytecode interpreted language. It's probably 30 times slower than, maybe 20 times slower than GHC. It doesn't really matter. It doesn't really matter because you can cache things. It's pure, so you can be very aggressive with caching and parallelization. You have fast, low-level libraries. And there's a reason Python's successful, right? Python's not a fast language, but it's the glue. We're using Haskell 98 as the glue over lots of different systems. So the things we really care about: latency, bandwidth, memory hierarchies. So you have the big compute farms, or maybe Amazon, then you have your local data center, and then you have local users, then you have nearby users, maybe in Europe, who are on, or maybe even in New York, or you're maybe 50 milliseconds away, 100 milliseconds away. And then you've got the people who are 300, 500 milliseconds away, and they've got lossy networks because they're in Kenya, and their network bandwidth's really limited. And they've got small disks, and then they've got remote memory, and then you're sitting in a thread somewhere very far away. So you've got this huge memory hierarchy of like 6 different layers, 7 layers, and you have to decide where the work should occur. So you start to care a lot about cost models, about knowing the size of the box that you're executing, and you end up with a lot of control flow and resource management APIs for timing things out, monitoring the resource usage, killing and restarting, moving stuff automatically upwards, up the hierarchy to somewhere where there's a bit more gas, a bit more space for the gas to expand to. It's amazing that you start thinking, oh, this just fits in a thread in the local process, and then you realize, oh, I've exceeded my process memory limit. I need more processors. Oh, I can't even fit on one machine now. I better move to a few more machines. Oh, I better go to the data center. Oh, the data center's full. I need to go up to Amazon and start using arbitrarily large amounts of compute resource. So we use a lot of memoization, and this is again because we have side effects are tracked, so we know stuff that's pure. We strongly prefer database schemas and persistent schemas that are versioned and pure and immutable. So we never throw stuff away if we can avoid it. So unique keys for everything that uniquely identify that value forever. You name every value that leaves your system, and it gets its own unique identifier. And if you modify it, you generate a new version. You don't delete the old version. So all references that leave your process continue to work forever. That's sort of the gold standard. And when you do that, then you can implement really aggressive memoization and caching. So I can read from a database once. I've got the reference. I store it locally. I keep it in memory, and then I keep it on disk, and then I never have to go back through the memory hierarchy to the original database to get this value again. Maybe I garbage collect locally every now and then. So you've got garbage collection happening at different levels, but you can cache super aggressively and exploit the purity, exploit the immutability to keep data around. So you duplicate data a lot. Don't worry too much about not doing that. And a lot of data moves very rarely, so you can cache it and avoid looking it up. So calendars, somewhat rarely, but there's lots of stuff that doesn't change very often. And the Mu compiler implements very early on, we've had the ability to serialize closures. So it's a double-edged sword because it's really cool. You can just take a value and save it, and then you can get the value back. And you can move it anywhere, and you build these crazy architectures of mobile code where a function goes here and some data goes there, and you apply them somewhere else, and you stream partial results and apply them again. And you can just imagine that's a playground for a Haskell programmer. But you also now have some bytecode that you serialize to disk in some format that's internal to the Mu compiler that no one can, it's not standard, it's not, is it going to work in 3 versions time as the compiler changes? So now you've got versioning, you've got serialization issues, it needs to be fast. So it reminds me of using lazy data structures for parallelism. So lazy channels, for example. The work tends to surprise you by migrating somewhere where you didn't expect it to because of the laziness. So the func didn't quite get demanded in the thread that you thought it was going to. It jumped over an exception handler and got evaluated outside of its context. And that's something you get a lot of powerful operations when you have lazy parallel programming with threads. You can move work anywhere and you can trigger it, but you also don't quite get to control it. And similarly, once you start serializing things, we sometimes serialize the wrong thing, but it still works, right? Everything serializes. So, oh, I accidentally serialized my GUI, not the data that was behind the GUI. And when I see the thing, I click on it, load the value. Oh, I got my GUI back. That's not what I meant. So you can just, there's not quite enough type structure there. So we're starting to do things like add prim types and so on to constrain the useful stuff to serialize. And a bit like with laziness, you have NF data and so on to demand that the data be in certain normal forms. We want to serialize only particular normal things. And process isolation, I've talked about this again. It's still incredibly useful, and we don't do it well in GHC yet. But the way in GHC Haskell, you have a great thread library, and you can spin stuff up and fork things. Imagine doing that with processes and nested hierarchies of processes with supervisors. And they're like a thread. They're a little bit more expensive to spawn, but they have guaranteed memory usage. You can poke at them from the outside. You can limit them using U-limits in all sorts of different ways. So you get very strong, and they're great for untrusted code. So if you have some pricing code or some weird network service that calls some database DLL that you don't trust, drop it in the sandbox, watch the process, let it fail. And so you keep your nice Haskell code apart from the really untrusted things. You've got your I/O on the edge, and then the really untrusted I/O is in a sandbox outside talking over a socket. So we restrict the impact of bad components with process isolation. And then you start to do cool things like retrying on failure, speculatively executing things. So just fork it and see if you might need it, but you spin it up in a separate process, so you're not even wasting memory in your core process, and you let the operating system deallocate for you. So we're not Erlang people, but we're sort of getting there with the amount of process isolation and monitoring that we're doing. We have trees and groups and nested map-reduced structures and trees of processes watching each other. Maybe thousands and thousands of processes sometimes. And we have a really great SVG library for plotting the dependencies between all the processes. You can imagine, once you've got a farm of these things, you need to actually watch who's executing and what state they're in. Okay, so the caveats. This is really fun. I mean, it's a really fun environment to program in. We've got a lot of Haskell code to do a lot of useful things, and we can build many, many useful trading tools for the company. So we bring real value to the company with this. It's clearly value that there's no other, it's a unique value proposition. But you need a lot of infrastructure to get there. You need, I didn't say Mu's not recursive by default. Recursion's disabled. It's a language feature because it's strict. So we don't want people blowing the stack with their, so that's interesting. You can write a lot of programs without recursion. And then you start to think, a bit like an Agda program, you start to think of general recursion as a dangerous language feature that you need to turn on. But we use concurrency and speculative evaluation, but we need fairly cheap threads for that. To migrate work, you need some way to serialize stuff. You obviously need a type system. So you can do this in Haskell, but if you've got a language that's close to Haskell, you can do a lot of these things. And you need a critical mass of experienced people who know what they're doing. Otherwise, you might be able to just do one system, but the amazing combinatorial benefit happens when you've got lots of APIs in the same ecosystem, all being type-checked together. And so you have a huge repertoire of things you can write and new things you can write. But you need a few people to get to that point. And even if the language has all these tools, and it's a great Haskell implementation, and it has all the type systems, you can still write Java. You can still write Java, and people do. People really do. You can IRF, put an IRF in a data structure. And now I'm not writing Haskell anymore. So, look for machine-supported ways to minimize complexity. That's the key, is minimize complexity as the system gets bigger. A very good way to do that is using types, to distinguish the things you trust from the things you don't trust, and to remove the number of ways systems can interact. The fewer paths components can talk to each other, the more comprehensible the system, the more likely it is you'll be able to quickly remember how to fix it and maintain it at 7 in the morning 3 years later. So try to think about what happens in 3 years' time when you come back to something and it's not working. That kind of machine support for keeping the whole system working lowers the maintenance burden, increases the chance that the first thing you write works, and means that we can deliver faster. And we do deliver faster. We deliver in hours, or 1 or 2 hours sometimes, for things that look hard. And this leads to a platform of things that you just reuse. So the Haskell code that comes out of one project gets reused by another Haskell project. And that's not always the case with large enterprise IT systems that are built. Two projects that never talk to each other rarely will share infrastructure in the future. But in Haskell, that's really easy. You just take a bunch of functions, drop them in a module, and name it, and then someone else can call it. So the reuse is extremely cheap. So the choice of programming language has a real effect on your results over time. It scales as the systems get bigger, and you start to get more and more benefits. There's not, a 1,000-line Python program and a 1,000-line Haskell program. Maybe you write them in around about the same time. Once you've got 2 million lines of Haskell and 2 million lines of Python, it's glaringly obvious that the machine checking helps keep this thing running. Stick to the basics. You get the vast majority of benefits. I haven't talked about GADTs. I haven't talked about any technology invented in the last 10 years. Except for a very brief mention of typed relations. So we try and remove the dynamically typed parts, and relational algebra was one thing we didn't have a type system for. So you would make runtime type errors. We want to remove those, and that required a pretty fancy extension to the type system. But you get most of the benefit just using new types, data, and functions. And certainly all the benefits of reuse and minimizing complexity were already there in 95 or earlier. So that's it. I'm hiring, I want to say. I'm hiring. We have 25 people on my team. I want to get to about 35 this year. There's about 7 roles in London, doing all sorts of things now. It's not just one project. There's low latency, there's data transformations, there's GUIs. There's a DevOps role to build this continuous integration system and extend our CI system. Talk to me, talk to Ben Ford. I think he's here in the audience somewhere. He's up the back. He's here. Talk to me, and otherwise I'll take your questions. Thank you.
Okay. You talk about logging and how important it is, which I agree with, and now I/O enforces sequencing while pure functions don't, and now, that's a big plus for pure functions. How do these two things fit together, though? Because I write a lot of this kind of code in Haskell, and I find that a reason for which I/O creeps into code is to actually have the sequencing and have a log of what's happening, right? Because then when I need to, especially as a human, when I need to understand what went wrong and when, I like the sequencing. And in general, can you give a comment on the problems and the solutions to, operational semantics is so far below the code in Haskell, right? And right. I find this is the biggest problem. I spent half of this week debugging this problem where we don't know what is executing, which is coding, we don't know the sequences of action that led to certain problems. And this happens more often in Haskell than in other programming languages because of this reason.
Right, so the key parts of your system need to be logged. The key, the business logic steps, the major functional steps have to be logged. If you really care about all the intermediate results of your computation, you need to externalize them from the computation. You need to put a side channel. So basically all your return types now have an evidence component. So we've written systems like that are, for example, for audit, for very regulatory sensitive code, you essentially build a trace of the computation alongside the computation. It's pure code. You return the whole thing at the end and log it. But we try not to break apart all our nice pure code just to insert log statements. So you log in units that make sense from the architecture's point of view, and then you accumulate evidence in pure computations where you do care about the intermediate states. I'd say that.
Hi, my name is Nick Wu. Thanks very much for your talks, very inspiring. And you've described a kind of utopian place where everyone seems to work and the code is brilliant and everything's fantastic. And I like that dream. But I wonder, what are the dark corners, and where do things go wrong, and when do you wish that you had another language, or that you were jealous of some feature that something else had that you don't?
Right. Yeah, it is. It's very nice. It is very nice because we've got a large Haskell code base. So you can do, sort of I was saying, that a lot of value can be done by keeping it simple. But I hinted at some of the issues. People cut cables and people reboot servers. So the things outside of your system, you are still to blame for, right? So your high-profile trading app fails because somebody snipped a cable somewhere. Who gets blamed? The high-profile trading app developer. My number is not here. What's the problem? So you have to be very careful with systems around you, and you monitor them and log them, and you have to essentially do other people's jobs for them in terms of monitoring, so that your system alerts when the systems it depend on fail. Don't trust them to send you notices. Make sure that you're really paranoid about it and logging. So do everybody else's job in terms of logging and monitoring, such that you can answer, when someone says it's your fault, you should be able to say exactly what went wrong and whose fault it really is. And one of the things we're doing now is actually stretching into more harder to get to places. So imagine using GHCI for low latency trading algorithms, it's probably not the perfect thing for that. And we're starting to look at sub-millisecond, sub-100 microsecond times. We're going to have to write this code in GHC because I need assembly. So there are harder problems. It's the same path that Haskell took. You could do a lot with the core language, and then we extend it into more and more specialized and rarefied domains where the resources start to matter. The available number of cycles, the amount of RAM, the footprint, the response times. And there you need to start restricting what code's running. But it's the last 10%. There's a lot of value already. You can just keep doing it in Haskell 98, and you would have a happy business of writing core trading software.
So you talked about compiling the world of 3.5 million lines of code. The question is, how long does it take to compile the world? And what tools do you use for development in general?
It type checks pretty quickly. You can type check the thing. Compiling and running the world and running all the tests takes hours if you want to check everything. So we do a nightly release of our code. But once you've got a whole program compiler, the first thing you want to do is start modularizing it and not type checking everything. So very early on, you start to split into, I've changed something, I only want to type check this area because I know it doesn't interact with anything. And more recently, we have separate compilations. So you start having components, essentially libraries that talk to each other. It's still more flexible than a fully static module system. It's more like plugins. I just get to choose pieces to load at runtime and pieces to compile separately and combine. So it's more like a module, an ML module system in a little bit. I don't want really, not in expressiveness, but in terms of the flexibility of any module I can take out and work out whether it loads statically or dynamically or at startup. So you start building. You have to end up rebuilding all the systems that exist in other languages to solve all the problems, because they all existed to solve some particular problem. And eventually you get to that problem and you're like, oh, I need that language feature now, or that platform feature, or this library. At the front.
You said is AST everywhere. Do you have any recommendation on abstractions or libraries to transform ASTs, and kind of so that the description of the transformation doesn't get obfuscated by the code itself?
We keep it simple. Haskell 98. Write a data type, write a transformation from that data type to another data type, and then enumerate using case analysis. So it's all induction on the structure of the AST. So really, really simple. We generate code in some cases, especially like lenses, for example. We just inspect the data type and spit out all the lenses. But I only write a new binding to a new system once, and so I just do it by hand. Case analysis, the compiler can check that I've exhausted all cases, and I've got one mapping from one data type to another, and I'm done. So keep it simple, and then anyone can maintain that code because it's not using some weird DSL for, decorating, generating, tagless, whatever. It's simple, really simple. The simplest Haskell is where 90% of the value is.
So you mentioned earlier in your talk that you're using in your company a lot of other languages. and only some things are being done with Haskell. Are there any parts of your system that you couldn't do in Haskell yet due to performance problems or maybe unpredictability of the garbage collector or something like that? Or is it just legacy
yes. No, I
code?
mean we're not doing low latency algos. So I can control things down to about 2 or 3 milliseconds. If it was 25 nanoseconds, I couldn't do that in Mu. If it was GHC, I would probably have a go at it if it was GHC. Yeah, I would not feel so constrained using GHC. But I can take the assembly and write primops if it's GHC. So, but then again, you also wouldn't use Java for that. You're in the world of specialized tiny language subsets with hard real-time constraints. That's an example of something where you probably generate code. GUIs as well, JavaScript's another one. I don't want to write JavaScript GUIs, I want to write Haskell code and generate the GUI. So, like, oh, I don't use Haskell to directly do these things, but actually I just use Haskell in a DSL and I generate the thing that I want to actually execute. So that's the hack to keep writing Haskell code, is write a DSL.
Okay, final question.
It's related to the last thing you just said. It's a twofold question. How long have you been using Haskell for user interface in the web? And what's your stack for that?
So we've got a few GUI libraries, but Neil Mitchell wrote an amazing library called Widget, which is it's a Haskell library for generating WPF GUIs on the desktop. And so that's been very useful for desktop software. It's broadly reminiscent of things like Cairo, GTK-HS, things like that. It's that level. You've got events, callbacks, layout and control, and logic, and you glue them together. We've built libraries on top of that for subsets of GUIs that can be declaratively described and just generate, for example, editors are an easy one. If I have a data type, I can generate lenses, and then I know the types of all the fields, so I can generate special editors for those fields, and you can generate the GUI, the lens, and the data type all from one description, and you're done. So you can derive GUI, essentially, for specific, simple problems. And that gets you something that works. But the problems with GUIs is every pixel matters, and you have to go back and specialize and specialize and specialize, and then you need all these little tweaks. So you have to be able to go down to low-level GUI things to build anything terribly useful with a lot of users. And so we have libraries for this. It's in-house. We use Cairo. We use Haskell plotting libraries. So some of the big components for generating things.
Okay, so one more thing, because Don brought up the topic of hiring. So I can imagine that he's not the only one in the room who is looking to hire Haskellers. So could all the people who are willing to hire Haskellers please stand up and show themselves? And just keep standing for a moment so that people that are looking for Haskell jobs can remember your faces and talk to you. Okay, I would like to thank Don again. We can continue the discussions in the break. Yeah, thank you.
Thank you.